Okay, so here's a little video on pedigrees. So this is using a slightly different app, so hopefully it works out for you. So it's a mixture of my crazy handwriting and some typing. So here's a little bit of vocab for you to go over and some things you should be able to do with pedigrees just to remind yourself, so you could pause and jot that stuff down and go over it in your notes. Okay, so we're going to use this one pedigree over and over again to go over some things. So just to remind you that females are usually circles and males are squares, and when we color it in, it's a trait. In this case, it is an autosomal recessive trait, and autosomal means it's not sex-linked. So autosomes are the other chromosomes, not the sex chromosomes. And so we have 4 generations here to look at, and this is an MCAS question, an old MCAS question we're going to go through. So who among these, and there's a couple you could maybe guess at, but one for sure, who could have a homozygous dominant genotype? And so you should pause and figure this out before you go to the next slide for the answer. Who can have a homozygous dominant genotype? And remember, this is not sex-linked, and we're using M's. So homozygous dominant would be big M, big M. And when I figure these out, I usually start with the shaded in traits, and I start at the bottom. So I would start with number 10 and go with little m, and work my way up. And that's been always the way that I've done it. And I usually figure out the Punnett squares along the way and map them out and figure out what the possibles are. Okay, so number 4 could be big M, big M. Okay, and if I want to check myself, I can do a Punnett square because I know number 3 is little m because it's shaded in with the trait. And if I do that Punnett square, I can see what the possible siblings are, and I see that that works out that number 7 would be a carrier, a heterozygote, so that would work out. Okay, anyone else? Might say that number 6 could maybe be a homozygous dominant as well. Okay, if 7 and 8 have another child, what are the possible genotypes of the child? So if 7 and 8 are going to have another child, what are the possible genotypes of the child? So to figure that out, you need to know the genotypes of 7 and 8. And so pause before you move on to get the answer. Okay, so the answer is basically all the possible genotypes. Homozygous dominant, big M, heterozygous, big M, and homozygous recessive, little m. Because 7 and 8 are both probably heterozygous, because if we do the Punnett there, that's the way we can end up with number 10 being homozygous recessive to have that trait. So those are all the possible genotypes for number 10. I hope this makes sense. I'm really tired. It's been a very long day. All right, and here's an open response. So remember I said that pedigrees are really common open response on MCAS, where you have to kind of work backwards and prove things with a Punnett square. So here's part of an open response from an old MCAS. Draw the Punnett square for 1 and 2. What are the predicted phenotype percentages for their offspring? B, compare the actual phenotypes with the, oops, it didn't all show up. The text box got cut off. Compare the actual phenotypes with the predicted phenotype percentages. So remember that Punnett squares are always a prediction of offspring. So we're using them to predict something. They're not the actual offspring. So we're often comparing them. So if we draw the Punnett square for 1 and 2, so remember that I said we would work backwards and always start with figuring out the recessives because we know they're homozygous recessive. So you would do that, and you would see that their two offspring are actually homozygous recessive, but their possible offspring would also include some heterozygous. So you would compare the possible percentages with what actually happened. I believe there was actually a part C to this too, where you would draw another Punnett square, but I didn't add in that part. So that's all you would do is compare the percentage of what's possible, and then say that when they had their children, they had each time they had a homozygous recessive, but each time they had a possibility of having 25% homozygous recessive. So it just so happened that they did have a homozygous recessive each time. So I hope that makes sense for pedigrees for you, and good luck.